Okay guys, so we continue topics in the linear system theory, and in the previous class we were talking about the diagonalization of an square matrix, n by n matrix, right? So we said that if we have a matrix A having distinct eigenvalues, and in the form of this, A is 0, 1 and 0, remember that, you name it, canonical controllable form, that's right, that we previously developed, that's right, and minus an minus 1 and minus a1, remember, this is canonical controllable form that I taught you in the previous classes, right? So if we can make it a diagonal matrix. So how? By this transformation matrix. So the transformation x is equal to pz, okay, where P is a matrix, is an interesting matrix of first row is 1, 1, 1, 1, 1, second row is lambda 1, lambda 2, that's right, until lambda n, and then lambda 1 square, lambda second square, lambda n square, until you get lambda 1 power of n minus 1, lambda 2 n minus 1, and lambda n minus 1 power of n minus 1. So you're going to ask me, what are the lambdas? Lambdas, as I taught you in the previous class, are lambda i's are n distinct eigenvalues of matrix A. Is it recording? Yeah, okay. So if you remember from the previous class, I said that you can find lambda I minus A, determinant of this is 0. We can find the eigenvalues from here. That's right. So by applying this, this matrix, this transformation will transform the original to this into the following form, diagonal form, to this following form, guys. So again, if your matrix is given that is A has a distinct eigenvalues, so we're gonna have P AP gonna be lambda 1, lambda 2 until lambda n, and here is 0 and here is 0. Understand? So take home message is that if given matrix A, B, C, D, whatever it has, multiple eigenvalues, because Jordan form, remember? Because in the Jordan form we could make it the state space representation, because the matrix has a repeated pole, 3 repeated poles. Diagonalization diagonalization is impossible. So you have to have what? A distinct eigenvalue. So example of that. Example, right? So suppose this is the matrix that you have 3 by 3 for a third order system. 0, 1, 0, 0, 0, 1, minus 2, minus 3, and minus 1. Huh? Right? So this has such a transfer function. If you look at the previous class notes, I don't care about here. So you're gonna have, because it's the controllable canonical form, gonna be S it's gonna be third order system, S cube, right? And this is plus 2s squared plus 3s and the plus 1. These coefficients go there, that's right. So, or we are reversing, guys. So I'm sorry. So it's going to be 1 and 3 and 2. See, this is how we made the controllable canonical form. If you go and look at your terms, it's a third order system, that's right. So what you're going to do, you have to find first eigenvalues of this matrix, guys. So I'm just doing these operations, and finally get this. So lambda minus 1, 0, 0, lambda, and minus 1 and 2, because you are multiplying by minus the matrix A, 3 and lambda plus 1, right? So we are finding the lambdas. So you know that this is how I find the determinant. You have to know from the algebraics, right? So it's gonna be lambda in this matrix. Determinant of this matrix is gonna be lambda plus 1 and minus plus 3, right? And then plus 1, because this is adjunct, that's right. So it's gonna be 0 and plus 2, and this is 0, right? So we get this. So you're gonna have simply you're gonna have lambda and lambda squared plus lambda plus 3 plus 2 is 0. So your equations. Oh, what the hell happened? Sorry, guys. Okay. So hold on. Sorry, guys. I have no product. I promise. So you're gonna have lambda cube plus lambda square plus 3 lambda plus 2 is 0. And this is the equation, or the characteristic equation, that gives you what? Gives you why I say characteristic equation? Just compare this with this. For this canonical controllable form. You see exactly this. Unexpected this, actually. That's why I'm saying, because in undergraduate control we name this as, if you remember, we name this as characteristic equation. So it's the same like that. That's right. Okay. Let's double check. Yeah. I never trust anyone, even myself. Okay. And this is 0 plus, yeah, okay. So you're gonna tell me how I solve it? It's very easy, guys. Here that you have to know MATLAB, guys, as I taught you, MATLAB. Okay, as MATLAB comes up, Okay, so you're gonna have let me, there's a glitch here, hold on. Okay, so how we do that? It's very easy. You have to say, you have a symbolic, say I'm saying x, but you can say lambda. That's right, because the parameter is based on, I'm saying lambda is x for simplicity. Sims x, and then you're defining a equation which is x cubed, that's right, plus, what is the equation? Plus lambda square plus x squared plus 3x plus 2 is equal to 0. That's right, this is the equation. This is how we define in MATLAB. That's right, the equation, our equation is this, is right. Here we go, we got here 1, 1, and 3 and 2. That's right. Then you're gonna go use this. S is equal to solve, okay, solve what? Equation, and the variable is x, and you're gonna say max degree of 3, because it's third order equations, right? So max degree of 3, and this is gonna give you this. But for making this understandable, I'm just putting, if I see, can I say double? Means, let me see what we get. So these are, double means that make these operations to pure math. These are the eigenvalues of your system: lambda 1, lambda 2, and lambda 3. Understand? Okay. And you see that one of them is real, and the other two are the complex conjugate. That we learned from the undergraduate control, right? So we have to make the matrix P. So matrix P is now based on whatever you now you have in, look at here. This is matrix P, guys. This is matrix P. That's right, matrix P. So, and because your system is third order, so the maximum power is gonna be 2. 3 minus 2. So what I'm gonna do, I'm gonna say is 1, 1, 1, 1. That's right. So lambda 1. That's right. S 1 and 1. S 2 and 1. Lambda 2. S 3 and 1. That's right. First, second row, third row, and the first column. That's right. So you see the second row, and now exactly this to the power of 2. That's right, it's squared. Here we go, and I'm going to square these, this, and this, right? Understand? So here we go. Then, based on whatever I taught you, if you find this, what is that? P inverse AP. So you have to say inv of P in MATLAB, inverse, multiplied by original A. Original A is what? Is, our example was 1, 0, 0, 0, 0, 1, and what was that? And what was that? Minus 2, minus 3, minus 1. That's right. And minus 2, minus 3, and minus 1. Now again multiplied by P. Here we go. You see that our A that was non-diagonal matrix, we transform to diagonal matrix. This, this, and this. And this is what? This is the first eigenvalue, second eigenvalue, and the third eigenvalue, and the rest are zeros. So we made that non-diagonal matrix to diagonal matrix. Okay? Clear? Okay. So here we go. Okay. So let us okay, guys, so now we can continue our topics. So after finding that in MATLAB, right, so there is another thing that you have to know. When you are transforming your matrix to a diagonal form or any other transformation, the eigenvalues of the matrix remains constant. So the name of this property is invariance of eigenvalues. So to prove this property, subject to a linear transformation, we have to show that eigenvalues of in this form, lambda I minus A, this gives you arguments of A, and its transform diagonal form that just we did for the example, which was P minus 1 AP. This made us what? Diagonal form of that matrix. Minus lambda I are identical. Okay, so let us do that together, guys. Okay, and the name of that is invariance of eigenvalues. So the original one is this original matrix, or we can start from here, guys. So after that transformation that we did diagonal for this case, minus lambda I, that's right. So, or this is like that, to be consistent, right? So now you can say I is what? Is P inverse in P minus P inverse AP. We can, that's right. Yeah. So you see that P inverse can be written as this: P inverse lambda I minus A in P. We got here P inverse, okay, P inverse lambda P, that's right, minus, lambda P inverse P minus P inverse AP, that's right. Can be simply written like that. So this can be written as what? This can be written as determinant of inverse of P in determinant of lambda I minus A in determinant of the P, because we know we have, generally we can know, and we know this from the algebra, that determinant of the matrix AB is matrix A in matrix B. That's right. So that's why we can write like that. Understand? So now we can write like this: P inverse, and move this here because these are the numbers at the end of the day. So it is lambda I minus A. That's right, determinant of lambda I minus A. Now, as we did here, we can do this here. Determinant of P inverse P, it is determinant of lambda I minus A. This is how much? 1. So at the end of the day, you get that determinant of original matrix is equal to determinant of its linear transformation. Understand? And it's a very, very important topic that you know. We are not changing the eigenvalues of that. So you're gonna ask me, okay, what we're gonna do with this? Why we have to know that by linear transformation, nothing here? Because the eigenvalues, as you're gonna see eventually, they are the roots of what? They are the roots of in the canonical form. They are canonical controllable form. They are the roots of the characteristic equation. Understand? So it's very important. So, and let's go to the MATLAB again for refreshing your minds if you don't know. If you have y over u, that's right, transfer function, this command in MATLAB gives you state space representation. Means, if you have the state space representation, this is gonna give you, have a state space representation, it's gonna give you y over u transfer function. It's gonna be S2 transfer function when you give A, B, C, D. Understand? Or sometimes we're writing a steady state to transfer function of A, B, C, D as your system single input or single output. That's right. Understand? So this is other things that you have to know. Okay, now let's go to deep mathematics of this course, because you have to learn lots of things before designing the controller. Okay, so we saw that we can generally have the state space LTI system, linear time invariant system, as AX plus BU. Suppose that there is no input to the system yet, so we only have the linear form of state space. X dot is equal to AX. That's right. Remember, guys, so I want to find the solution of this. Okay, is a dynamical system. Remember that in differential equation, if you had such a just as like as AT, because A here is a matrix, that's right, here is matrix, but in differential equation this was the scalars, right? So how we were solving this? Oh, sorry, X. How we were solving this? We were assuming that the general solution X is equal to ESD, that's right. Then the first time derivative gonna be S ESD, and then replacing here you're gonna have S ESD is equal to A ESD, right? Or ESD is S minus A is 0. This never ever cannot be 0. Why cannot be? Because if that's 0, you have the trivial solution of 0. So from here you had S is equal to A. So the general solution of this equation X of t was EAT. But A here again is a number, scalar, not matrix. But with the analogy between this differential equation and this differential equation, you can simply say that if you have the state space form, X dot gonna be E A matrix T in X at the initial conditions at time 0. So the solution of that gonna be this. It's very simple to understand. But we have to know what is this exponential matrix. The name of this exponential matrix, or matrix exponential, right? So you have to know that. It is very easy, guys. Remember that Taylor series expansion that was f of x, f at equilibrium point plus round f over round x at the equilibrium point. Here is, suppose here is 0, and x minus 0 plus 1 factorial round second over round x square. X is 0 at x minus 0 power of 2, and continues, right? So let us hold on, they have a glitch here. Yes, yes, and you have 2 factorial here. Forgot to do that. That's right. So Now I want to find this matrix exponential using the Taylor series expansion. So see, EAT, your variable here is t, not x, is e at time 0, a0, plus its time derivative with respect to time. Your x is time here. Your x is time, that's right. So it's gonna be a e a t at time 0 at t, here t, plus the second time derivative gonna be a square, that's right, e a t over 2 factorial, again at time 0, now t square, and continues, that's right, a cube e a t at 3 factorial, again at time 0, time cube, and continues. First of all, A is matrix. You cannot say that this is 1, because e to the power of 0 is going to be unit matrix. That's right, identity matrix. Understand? So this is I, not 1. So this is going to be again I, this is going to be again I, so plus AT plus again a square t square over 2 factorial plus a cube t cube 3 factorial until a is matrix again, tn over n factorial. So you can approximate that this exponential matrix by Taylor series expansion, and finally you can say EAT matrix exponential is, which is solution of this state space equation, that's right, which is sum of, as we know because we are summing, that's right, sum of k from 0 to n, 0 to n, that's right, I'm sorry, and because we have infinity things, or to infinity because we have too many things, so ak, because tk, as you see exactly, divided by k factorial, that's right, k factorial. So now you know that, oh, I'm stupid, this is x of t, guys, right? This is a solution like this. This is not x dot. It was a typo here. So you saw that this linear time varying without any control input solution gonna be x of t, gonna be what? Sum of k from 0 to infinity ak tk divided by k factorial at the state variables at the initial condition at time 0. Here we go. Bingo. Bingo. You found that. That's right. But now you're going to ask me, Payman, you're telling me that the first time derivative of EAT is A matrix A EAT. How is that possible? We know from the scalar version, but I want to see the proof of that, how that's possible. So first of all, I'm writing everything here, guys. I'm writing everything here, saying that if you have this LTI system without control input, A is matrix, and this is state space representation, as I taught you. So its solution again gonna be this state variable at time 0 in sum of k from 0 to infinity ak tk over k factorial. Guys, ak is not every element, that means a k time, okay, k time, that's right. So get this matrix. So now if you look at here, I told you that the first time derivative of this is gonna be this. You have to see how it's possible. So it's very easy because I taught you the Taylor series expansion, guys. So if I want to see the first time derivative of matrix exponential at, I want to see that. So based on whatever I developed, hold on, I have to fix this.